So now we started with this idea of quadrants, and then we got to the sample covariance. And the sample covariance led us to this quantity called R, which is the sample correlation. Again, it's just derived from this idea of the quadrants. Now I'm going to define another quantity, which is actually the one we've been aiming for. The estimated slope of a linear regression line is going to be a function of the correlation. In particular, it's going to be the correlation times the ratio of the two variables' individual standard deviations. So this is an important result, right? What are we finding? Well, initially, we wanted to understand the relationship between these variables, so we made some quadrants and we tried to think about how many points were opposed as opposed to adjacent. We turned that idea into a sample covariance. We divided the sample covariance by Sx times Sy and called it the sample correlation. So the sample correlation R is just still related to these quadrants. Now I'm going to take R and multiply it by this ratio of standard deviations. And I'm going to call that the estimated slope of a simple linear regression line. So what are we seeing here? I'm going to write it in words because it's important. The estimated slope of a linear regression line is just a version, it's derived from, it's just a version of counting the number of points in each quadrant. That's where it comes from. And that's one way to understand it. So now that we have this relationship, let's see if we can come up with a specific equation for beta 1 hat, because that was our goal. We wanted to figure out how to use our data set to estimate the slope of a simple linear regression line. So this implies that beta 1 hat is equal to, well, let me write down what R was. So R was the sample covariance. So xi minus x bar, yi minus y bar. Whole thing divided by the sample standard deviation of x times the sample standard deviation of y. That's R. And now I'm saying the beta 1 is equal to that times the standard deviation of y divided by the standard deviation of x. Okay. So I see some canceling that I can do here. It's always nice to have a little bit of cancellation. So this whole thing is equal to, I'm going to write the numerator again, 1 over n minus 1 times the sum over the data points of xi minus x bar times yi minus y bar, divided by, well, the sy's are gone, but I've got two sx's in the denominator. Now that's the sample variance of the x's in the denominator. So another way to talk about the estimated slope of a regression line is that it's the sample covariance divided by the sample variance of the x values. Okay, but let's replace sx squared by what it's actually equal to. So we've got, again, writing the numerator again, the sample covariance, 1 over n minus 1 times the sum over the data points of xi minus x bar. Let me write that more clearly. Xi minus x bar times yi minus y bar. Whole thing divided by, well, what is the sample variance? You know how to calculate a sample variance, right? You add up over all the data points, the individual values minus the mean, and you squared them, and you divide by how many there are minus 1. Okay. Hey, I see some cancellation here. Okay. But now what we've obtained is actually the most common way to express the way to estimate a linear regression line's slope. The sum of xi minus x bar times yi minus y bar divided by the sum over all the data points of xi minus x bar squared. Okay. We derive that from the simple idea of trying to distinguish between the 4 quadrants. That's where this numerator comes from. The estimated slope of a regression line is just correlation standardized. The estimated slope is just the sample covariance multiplied so that it has the right units, right? That's all. So this is the expression that we're going to be dealing with as we think about different ways to understand it, but I've tried to give you one way to understand it so far. Here's a question for you. If sy is equal to sx, in other words, if the two variables you're looking at, x and y, have the same standard deviation, what is the estimated slope of that line?